Hello everyone, and welcome to our presentation. We are a team of 3 members, Phạm Thu Hà, Nguyễn Thị Thùy Linh, and Vũ Kim Minh. In this video, we would like to share with you our topic, the memory management models of the MIPS32 architecture. We hope this presentation gives you a clear and concise overview of how memory is managed in MIPS32 and why it plays such an important role in computer science systems. Let's get started. Now, here is the table of contents for our presentation. Number 1. Literature review of memory management in RISC and MIPS32. The second, the methodology. Third, results of analysis and experiments. Number 4, discussion and interpretation of future work. Let's begin with the first part, the literature review of memory management in RISC and MIPS32. The MIPS32 architecture is known for its flexible and efficient memory management system. It features a versatile memory management unit, also called MMU, that supports multiple techniques for translating virtual addresses into physical addresses. Some of the key schemes include translation look-aside buffer, known as TLB. This is used for fast address translation, helping the system quickly access frequently used memory addresses. We also have block address translation, also called BAT. This scheme is designed to efficiently map large memory regions, making it suitable for high-performance applications. And the last, we have fixed mapping, used for simpler use cases. Fixed mapping provided a straightforward way to manage memory without the overhead of dynamic translation. Let's move on to part A, the memory management in MIPS32. The MIPS32 architecture uses a memory management unit, or MMU, that is primarily based on a translation look-aside buffer, also known as TLB. This TLB plays a crucial role in the system virtual memory management. It stores recent mappings between virtual addresses and physical addresses, which helps reduce the need for frequent page table accesses. As a result, MIPS32 achieves faster address translation and better overall memory performance. This design makes MIPS32 well suited for both embedded system and general purpose computing that rely on speed and efficiency. In addition to the TLB, MIPS32 supports block address translation, also known BAT, which is useful for mapping large, contiguous memory blocks efficiently. For simpler systems, fixed mapping is available, offering a static and straightforward approach to memory translation. These memory management strategies have been widely studied and applied in real-world systems, each demonstrating distinct advantages depending on the specific application requirements. Compared to other RISC designs, MIPS32 offers more advanced memory management, making it suitable for both embedded and general-purpose systems. In contrast, the ARM Cortex-M series use a memory protection unit MPU instead of a full MMU. It focuses on simplicity and low power, ideal for basic embedded tasks. RISC-V is highly flexible, but many basic cores make virtual memory optional. Full memory management features are only found in more advanced implementations. These differences reflect each architecture's priorities and target applications. Let's move on to the summary of the first part. The memory management approach in MIPS32 integrates TLB, BAT, and fixed mapping techniques, offering a distinctive combination of adaptability and performance. This architecture provides more comprehensive support for virtual memory and multitasking than what is typically available in ARM Cortex-M or standard RISC-V implementations. However, these advanced capabilities come with the trade-off of increased system complexity and implementation effort. Let's move on to part 2, methodology. To begin with, we conducted a theoretical analysis to understand how the memory management unit, also known MMU, functions in the MIPS32 architecture. Specifically, we focused on 3 key mechanisms. First, the translation look-aside buffer, TLB, a small cache that helps speed up address translation by storing recent mappings. Next, we examine block address translation, BAT, which is used for efficiently mapping large blocks of memory. And finally, we looked into fixed mapping schemes, where predefined memory regions are used for simpler and static address translation. Together, these components form the foundation of how memory is managed in MIPS32 from a theoretical perspective. In addition to theoretical analysis, we also carry out practical simulations to test how these memory management concepts work in real scenarios. To do this, we use 2 main tools. First, the MARS MIPS simulator was used to run assembly level code and observe how memory operations are handled. And second, we use QEMU, a hardware emulator, to simulate a full MIPS32 system. This allows us to observe TLB behavior and memory mapping in a more realistic context. To support this, we designed specific test cases that trigger scenarios such as TLB hits and misses, BAT mappings, and fixed mapping conditions. These simulations have verified the theoretical models and provided insights into how MIPS32 handles memory in practice. The next part is data collection. During the simulation process, we also collected key performance metrics to evaluate memory management efficiency. Specifically, we recorded TLB hits and miss rates, memory access times, and the number of CPU cycles consumed. Where possible, we also compare the result with similar simulation on ARM Cortex-M and RISC-V architectures. This have highlighted the differences in memory handling across RISC platforms. To conclude Section 2, methodology, we now present the tools used throughout our analysis and simulations. Here, we have shown you a table with 6 tools we have used. We have MARS MIPS simulator, QEMU emulator, official MIPS32 documentation. Also, we have LaTeX, Overleaf, Git and GitLab, diagramming tools, Conclude.io, and Inkscape. The purpose and description you can see in this table.
So let's move on to the section 3, results. The first one in part A, TLB hit rate and success latency. Simulation experiments were performed using both the sequential and random memory access patterns to evaluate TLB performance. So what is the TLB hit rate? This is the percentage of memory accesses where the virtual address is successfully found in the TLB, resulting in faster access. Looking at this table, we can find that the sequential address show the highest hit rate 90% because the memory addresses are close together and likely preloaded in the TLB. Moreover, random address has slightly no hit rate 90% since addresses are unpredictable and less likely to be catched. In the TLB MIPS simulation, the hit rate dropped significantly 60%, leading to higher address latency. Therefore, the TLB is the most effective during the sequential access. In part B, we study the comparison of memory management models. The performance of TLB-based MMU, block address translation (BAT), and fixed mapping was compared using simulated workloads. So looking at this given figure, we can have some comments. The first one is PAT mapping provides minimal overhead for large and contiguous memory regions, making it ideal for real-time system. Moreover, fixed mapping offers the lowest latency but lacks flexibility and protection, which is suitable for simple embedded applications. So next, in part C, we study the comparison with other ISC architecture. We have the table 4.2, compare the memory management features and performance of MIPS32 and ARM context M and ISCV. It's easy to find that MIPS32 stands out for its support of virtual memory, high TLB efficiency, and real-time performance, make it ideal for multitasking. Meaningly, ARM can take an excelling simple real-time application, while ISCV produce a balanced and customizable solution with high flexibility. Therefore, we have a summary. The results confirm that MIPS32's memory management models, especially the TLB-based MMU and BAT, provide a strong balance between performance and flexibilities. TLB hit rates are high. So the final part is part 4, discussion and analysis. In part A, we study the interpretation of result. We have 3 models, TLB-based MMU, BAT, and fixed mapping. Firstly, TLB-based MMU, which provide robust support for multitasking and memory protections. High hit rate need to no latency, but TLB misses can cause delays. Next, BAT, which is excellent for mapping large, contiguous memory block, reduce translation overhead in real-time system. The third is fixed mapping, which offers predictability and speed, but lacks flexibility and protection. In part B, we study the significance of the findings and limitation. According to significance, MIPS32 hybrid approach allows it to serve both embedded and general purpose markets, outperforming ARM context M in flexibilities and ISCV in maturities of memory management. Meanwhile, according to the limitation, TLB size and refill latencies can limit scalabilities for highly concurrent systems. Fixed mapping is unsuitable for complex OS requirements. In conclusion, we have a summary, which is the combination of TLB, BAT, and fixed mapping give MIPS32 a unique advantages in adaptability and efficiency. Thank you for your listening.